Welcome to Strength of Materials and 6. Today's video is a video on shear stress in beams, and we will speak particularly on shear flow. This is a section that I had left out in my previous video on shear stress in beams, and the reason for that was because I did not want to make that video too long. And the second reason was that when I looked at the past papers until that point, I had not seen a question on shear flow in the exam. But it turns out when I looked at the paper that was written in April this year, that the question on shear stress in beams was actually a shear flow question. And for that reason, I feel compelled to also produce a video on shear flow. Okay, so this is what this video is about. It's just a continuation of the video on shear stress in beams. Let's begin. So what is shear flow? Shear flow is basically shear force per unit length, okay? So we use the small letter Q to refer to the shear flow, and the equation for that is that Q is equal to the shear force multiplied by the first moment of area divided by the second moment of area, or the moment of inertia. This is the equation you use to calculate shear flow. And the way we calculate shear flow is very similar to the way we calculate shear stress. In fact, when you look at the equations, they are very similar. The only difference is that for shear flow, we do not divide by the width, B, okay? And so, but when it comes to the calculations for shear flow and how to find the shear flow of a particular section at a particular point in the section, the way to go about doing that is very similar to the way we did shear stress. And so if you haven't watched the first video that I did on this particular module, I will strongly advise you to go back and do that, because in this video I am going to assume that you understand everything that we did in that first video, because this is just building up on that, okay? And so the unit for shear flow is Newton per meter, okay? And Q here, you will remember, it's the first moment of area. So we calculate it by summing the products of different areas and the distances of their centroids from the neutral axis, okay? So basically, if we write it mathematically, it looks like that. So Q is equal to the sum of areas and the sum of the products of areas and their distances from the neutral axis, the distances of the centroid of those areas from the neutral axis. If you watched the first video, you understand perfectly how to use this equation. Okay, so the direction of the shear flow must always be consistent with the direction of the shear force, okay? So you can think of the shear flow as being a flow of water, and that water will flow in a way that will be consistent with the direction of the shear force. So for instance, if we look at this T-section that we have here, you can imagine shear flow as being water coming in from this side and then from that side, and it has to flow in the direction of the shear force. So if we have a shear force that is pointing down, and then you have water that must flow in from here and from there, for it to flow in such a way that it will be consistent with the direction of the shear force, from the left, it must flow in this direction, as you can see here. Okay, it must flow in that direction from the left, and from the right, it must flow in this direction. Okay, as you can see, from the left, it must flow like this, from the right, it must flow like that, so that when this flow of water comes here, then it will meet and then fall down like this in the direction of the shear force. Okay, so that's how you see the direction in which the shear flow is moving. Okay, and so there it will be down like that, so that it can be consistent with the direction of the shear force. So here it must come like this, and here it must come like that, so that down here these two flows will sum up and then fall down together. So if you want to find the shear flow here, for instance, okay, somewhere here, this will pretty much be the sum of the shear flows in this direction plus the shear flows in that direction. Okay, but you do not need to divide your calculations like that. You can just do a similar thing to what we did when we were calculating shear stress, and you can just try to find what will be the shear flow here, by using the top area here and also the distance of this top area from the neutral axis of this section. Okay, so you just use the same approach that we did when we were calculating shear stress, except that for shear flow, the equation that you're referring to will be this one here. Okay, but here this is just to illustrate how you find the direction of the shear flow. Okay, so let us look at another section. Okay, so you have this section here, and so if the shear force is pointing down, if you want the shear flow to be consistent with the direction of the shear force, beginning here, you will want it to flow like that, so that when it comes here, it will flow down and be consistent with the direction of the shear force. And if you think of shear flow as a flow of water, so if it's falling down, then here it must go in that direction. And that's very much what you have for the direction of the shear flow when you're looking at the section like that. Okay, and as an exercise, we will look at a more complicated section, something that you are very unlikely to get in your exam, but just for the purpose of understanding, I have it here. So let's say you have a section like this. If we want to understand the direction of the shear flow, if the shear force is pointing down like that, how is it going to be? So if it is flowing from here and from here, of course, if it must be consistent with the direction of the shear force, then the shear flow must be going down. Even here, it must go down, okay? So this is what you will have. It's going down on that side like that. And on the other side also, it will have to go down like this. And I told you to think of it as a flow of water. So if this stream comes here, and that stream also comes down this way, when they get here, they will meet. And here you will have the sum of both streams that will be going down, okay? And that is why actually my arrow sizes are different. It's because the magnitude of the shear flow increases as you move, okay? And so here it will be down like this, okay? You will have the sum of these two streams here, and so the shear flow will be much bigger here, and it will go down like that. But as I said, think of it as a stream of water or a flow of water. And so when it comes here and you have this T-junction, if you want to think of it that way, it will have to split here. So some of it will go in that direction and then some of it in that direction, okay? Like that. So that's what you have pretty much. And so I hope with these three examples, you can understand how the shear flow direction is obtained. Okay, it might not necessarily be useful to you in terms of solving an exam question, but it is always good to have perfect understanding of the theory, as it helps you to also solve problems better. Okay, so moving right along, so now we will look at shear flow and fasteners, and this is where most of your exam questions will come from. Okay, so it is possible when you understand shear flow to be able to relate the distance between fasteners to the number of fasteners that you need for a particular section. Okay, and for that we use this example here. Okay, this is just a picture that I obtained from the internet. I will use this to try and drive the point across. As you can see in this picture, you have two I-beams. Okay, you can see this, you have the first I-beam here and the second one there, and then these two I-beams have been joined together by means of fasteners. Okay, so you have this plate that was put here, and you have 8 fasteners that have been put here to join it like that. And on top also they put a plate there with a number of fasteners, and at the bottom they did the same thing. They put a plate and a number of fasteners. Okay, and this is just so they could join these two I-beams. Okay, and so this is the sort of thing we're going to talk about. But like I said, it is possible now to relate the distance between the fasteners to the number of fasteners you need using an equation that has got shear flow in it. And the equation I'm talking about is this one. So S is equal to capital C multiplied by N and divided by Q. And so in this equation, S is the longitudinal spacing of fasteners. And in most of your questions, they may refer to that as the pitch, okay? So what do I mean by the longitudinal spacing of fasteners? Okay, so if you look at the picture here,